students, now we reach at the end of this chapter, electric charges and field, and this is our last application of Gauss law. Now at the end, application number 3rd or app 3rd, electric field due to a uniformly charged thin spherical shell. Remember, it is a shell, not a sphere. So now look at here. Now this is my thin spherical shell. You can consider this particular thin spherical shell, okay, like an envelope. So here you can see I already given a particular uniformly charged. So what is the concept today? We are going to find out the electric field due to this particular positive electric field lines, because as per the nature of this positive charge, electric field lines are coming outwards. So here we can find this particular electric field intensity at outside this particular spherical shell. Now at the particular surface, suppose here we can consider a particular point where we have to find on the surface particular electric field intensity, and now at the end when we open this, so it is behave like a spherical shell. So we can consider also the electric field just inside the particular spherical shell. So I hope you understand what is our aim for today derivation. As per the example, this particular derivation we will divide in a 3 part. First of all, we can consider particular sphere, spherical shell. So when we give the positive charge here, so all the electric fields lines are spread out, and we can find out electric field intensity at, first of all, just outside. We can consider outside of this spherical shell a particular point where we have to find the electric field intensity. Second, on the particular surface, and third, inside. So right now we are going to a very important part, derivation part. So please look at here. First of all, I consider here one spherical shell, and the particular charge over here like that, uniformly distributed on the entire surface, because this is a property of electric charge. So when we give charge to a particular surface, particular object, so it is uniformly distributed over the surface. So by the nature of electric field lines, the electric field lines are spread out in all 4 directions, like here also, like here, this one also we can consider, and like here. So first of all, we are going to consider the particular spherical shell of radius capital R, and from the center at the distance r, we consider till here, at distance r, we consider one point P, okay, where we have to calculate electric field intensity. सिंपल सा मीनिंग ये है कि एक पर्टिकुलर शैल को अगर हम चार्ज देंगे तो उसके एक पर्टिकुलर आर डिस्टेंस के बाद आउटसाइड, जस्ट आउटसाइड, आपको पी पॉइंट पर उसका इलेक्ट्रिक फील्ड इंटेंसिटी पता लगाना है कि कितना होने वाला है. ठीक है. सो नाउ फर्स्ट ऑफ ऑल, अब इस पूरे स्फेरिकल शैल को कवर करना है. सो कवर इमेजिनेशन surface known as Gaussian surface. So definitely here perfect Gaussian surface is sphere. So we can divide this derivation into 3 parts. First of all, we consider the electric field intensity at outside of the sphere. Then second one is at the surface, and third inside the sphere, because it is a spherical shell. So right now we are going to start derivation. Now here, first of all, flux through the Gaussian surface. the particular point P which is outside the spherical shell. So we know that phi will be just equals to E and A, the particular closed curved surface area. And now we know that here for a sphere, the area of a sphere is 4 pi r square, and here the particular point for Gaussian surface means from the center we have to calculate the electric field intensity at the r distance. So here in this condition, here area of a sphere is 4 pi small r square. This one is a very important point. So we can write here phi equals to E 4 pi r square, give the equation number 1. Now very simple, same step like application number 1 and 2. So now by very important person, by Gauss law, we know that phi will be equals to Q by epsilon naught. Give the equation number 2nd, and same steps by the equation number 1st and 2nd we can write E 4 pi r square equals to Q upon epsilon naught. Now E will be Q upon 4 pi small r square epsilon naught. So this is a particular electric field intensity at the point P, which is just outside of a charged thin spherical shell. Part of this derivation, here we consider a point P lies on the spherical shell, means a particular point just only lies at the surface. So here we can see again in this particular case, here on this spherical shell, I want to find out the particular electric field intensity on this particular surface, So let's start. Right now we are going to find out the electric field intensity, a particular point on the charged spherical surface. So same steps, nothing is new here. Electric flux, look at here, electric flux, same step, say, please say, electric flux, phi equals to E A, and right now what is the area of the sphere remains same, but right now here, because before we take r a particular distance, but here the radius is capital R, so here the area will be 4 pi capital R square for this. So now we can write phi equals to E, now 4 pi capital R square, give the equation number 1st. Again by applying Gauss law, phi will be phi equals to Q by epsilon naught, give the equation number 2nd. Now again the equation number 1st and 2nd, because the left hand part remains same here. So E 4 pi capital R square will be equals to Q by epsilon naught, and now E will be Q upon, now E will be Q by 4 pi capital R square, this is very important, epsilon naught. So this is a particular electric field intensity at point P which lies on a spherical shell. Now the third case is very important. So look at here, first case just outside here, first case, second case is just on the surface. Now suppose the P point is inside the particular spherical shell. Now third point, when the point P lies inside the spherical shell, that means this particular third one point. I am going to find out electric field inside this particular spherical shell. Same step. First of all, electric flux phi equals to EA, and the area will be same because we here consider the radius R. So phi will be equals to E 4 by capital R square, give the equation number 1. Now by Gauss law, phi will be q by epsilon naught, give the equation number 2nd. Same step, equate equation number 1st and 2nd. But wait, look at here, any charge inside this particular spherical shell? No. Why? Because we know that as the property of charge, when we give the charge on the body, so as per the nature of electric charge, all the charge just spread entire the surface, just uniformly distribute entire the surface. This is a property. And here, as the property, electric charge doesn't go inside the particular surface, so here q will be equals to 0. So right now when we equate also, because q is 0 here, so phi also 0 in this case. Now say the equation number 3. Now when we compare the equation number 1st and 3rd, so we can say phi will be equals to e 4 pi capital square will be equals to 0. That means phi will be 0 when the point P lies inside the spherical shell. So after this particular 3 case, this particular derivation has been completed now. Example point of view, and when we just talk about the previous question paper, one question also attached with this particular derivation. Just find out the nature of a graph between electric field and the r distance for the particular thin spherical shell. So here we can consider all 3 cases. First of all, when the P outside this particular spherical surface, so there is electric field is q by 4 pi small r square epsilon naught. When the point P just on the surface, this particular point P on the surface, so there is electric field q and 4 pi capital R square epsilon naught. And in the 3rd case, look at here, when P just inside it, so E is 0. So you can easily see that in the all particular 1st and 2nd case, we can say that one important thing, electric field is just inversely proportional to the distance. So we can say that yes, E is inversely proportional to the R square and follow the inverse nature also. So when we are going to plot the graph between electric field and the distance, look at here, so it will look like that. Here we can consider here particular E will be 0 inside the particular spherical shell. So here till here the electric field is remain same, okay, and because this inversely proportional nature just outside of the spherical shell surface, the electric field nature will be going to decrease like that. So this is a particular graph between electric field and the distance, which we can represent like that way. So here this particular derivation part has been completed here, and now the next section is problem solving session. So we are going to solve some numerical related to this particular application. A conducting sphere of radius 10 centimeter has an unknown charge, means charge we don't know. So here first of all unknown charge, to give the question mark, and the radius r is given here 10 centimeter. So first of all note down in a setup part. So first thing we already know, radius is a 10 centimeter. Quickly change the SI. So we can write 10 into 10 raised to the power minus 2 meter. Okay. And the charge we don't know, so give the charge is a question mark. If electric field 20 centimeter from the center of the sphere is, so electric field is given here 1.5 into 10 raised to the power 3 Newton Coulomb inverse, and the points radially inverse, what is the net charge on the sphere? So conditions like that, a particular spherical shell and the particular radius is here 10 centimeter, and up to that particular from here 20 centimeter distance, we have to calculate the electric field at this point, and we don't know what about the charge over here, and electric field is given to us here. Okay, so the particular problem is like that way, and already given that the electric field is 1.5 into 10 raised to the power 3 Newton Coulomb inverse, and the points radially inverse. So nothing here. So the particular problem is related to the concept of electric field at the point P, and where the point P lies outside the spherical shell, the first part of a particular derivation. So yes, we have to connect all this particular physical quantity by the formula E equals to Q upon 4 pi r square epsilon naught dot b. Here don't be confused about 10 centimeter because r the particular point, just we have to take outside it. So here we place the value. Now because the charge is unknown and we have to calculate the net charge, means here we can rewrite the formula Q equals to E 4 pi r square epsilon naught. After this step we are going to place the value, so implies that Q will be equals to E. Now wait, we can write together 4 pi epsilon naught. Why? Because we know the particular value of this, and here we know that 1 upon 4 pi epsilon naught will be 9 into 10 raised to the power 9 Newton meter square Coulomb inverse square. So we can put the value like that, Q equals to E 1.5 10 raised to the power 3 cube Newton Coulomb inverse, and this will be 9 into 10 raised to the power 9 Newton meter square and Coulomb inverse square, and the value of R, because this R will be 20 centimeters, so in a SI form 0.2 meter square. So right now this one meter square and this one is cancelled, Newton and Newton cancels and cancels, so it answer will come in a Coulomb. So Q will be equals to like 1.5 10 raised to the power 3 and upon 9 minus 9, and here we can write like that 0.04 after square, then we also can write like that. So here and here also this one like that. So answer after this, so we can write 2 by 3 is 0.66. So 0.66 into 10 raised to the power, here is a minus 6, and here is a plus 2 and minus. So it will be 0.66 into 10 raised to the power minus 8 Coulomb. So this is a particular net charge on the sphere. After watching this particular video lecture right now, I am going to ask one question for you, and after watching this video you have to answer it. इस वीडियो लेक्चर के एंड में आपसे एक क्वेश्चन पूछने वाला हूं, और इस पूरे वीडियो देखने के बाद आपको इस पर्टिकुलर क्वेश्चन का आंसर देना होगा. योर क्वेश्चन इज हियर, प्लीज सॉल्व इट एंड गिव आंसर as soon as possible. So conducting sphere of radius capital R equals to 20 centimeter is given a charge Q 16 microcoulomb. So what is the electric field E at the center? A 3.6 10 raised to the power 6 Newton per coulomb, B 1.8 10 raised to the power 6 Newton per coulomb, C 0, D 0.9 10 raised to the power 6 Newton per coulomb. Please write your answer. So please just quickly write your answer.